Hey, how you doing? Welcome to the next lesson in investigating the stationary point. Okay, you should have watched the first one on the table method before this one. All right, this one I'm going to be looking at the slightly more challenging one of using the second derivative to investigate what the stationary points are doing. Okay, now here's a couple of things that you need to remember. With the second derivative, just a quick table. If y double dash, second derivative, is, less than 0, not equal to 0, if y double dash is less than 0, right, that tells us that we have a max point. That implies a maximum point, right? If y double dash is greater than 0, meaning positive, that tells us we've got a minimum point, okay? And if y double dash is equal to 0, right, it doesn't really tell us anything. What you'll have to do is revert back to the table method in order to investigate what is happening with the points, the stationary points. Okay, so let's take a look at something quickly just to illustrate this. Okay, so if we've got find the stationary points for y equals 3x minus x cubed. Okay, well, cool. So this is our idea, and now what we have to do is we have to go into our second derivative. So let's just do y dash first. Y dash equals 3 minus 3x squared. You still with me? Okay. And then our second derivative is y double dash is the derivative of 3 it goes, the derivative of this is negative 6x. Are you with me? Awesome. So that's our second derivative for this guy. Now let's take a look at what happens for my stationary points. Now, here's the thing. We first need to find the stationary point, so we have to solve where this equals 0. So we have to solve where 3 minus 3x squared equals 0. Okay? Well, if we factorize out of 3 and divide it out, we get 1 minus x squared equals 0. Difference of two squares. 1 is a perfect square. So we've got 1 minus x, 1 plus x equals 0. Difference of two squares. This gives us our two solutions. X equals from this one 1, or from this one x equals negative 1. Perfect. Awesome. Fantastic. So there's our there is the x values of our stationary points, not the stationary points. If I wanted the actual stationary points, I'd take that value, plug it back into here, and get another coordinate. Okay. Right. So now we've got our two stationary points. Let's take a look at what kind of stationary points they are. Right. So the first thing I'm going to do is I'm going to take this route. Okay, I've done it backwards in the other one, but let's start with that one. It doesn't make a difference. I'm going to take that root, I'm going to put that into this one. So negative 6 times by 1, right? Not root, stationary point, coordinate. Root of the derivative, coordinate of the other one, right? So I get negative 6. Okay, so what does that tell me? That tells me that if this is negative, less than 0, it means it's a local minimum. Less than 0, local maximum, okay? So the point 1, and if I put 1 into here, let's just see what I get. 3 minus 1 is 2, 1, 2. Okay, I just plug this straight back into there, the 1 into there, is a maximum, right? Because it's less than 0. Then if we take y double dash and we put in the other coordinate for the stationary point, y double dash, and we put in negative 6 times by negative 1, this stationary point, and you get positive 6. Put negative 1 into here, negative 1 cubed is negative 1 times 1 is positive 1, right? 3 times negative 1 is negative 3 and positive 1 is negative 2. 1 negative 2 is a minimum. Everyone with me? Awesome. Okay, so that's very easy, right? Cubic, 2 turning points, 2 stationary points in the cubic. Okay, 1 less than the order, all right? And therefore max min. Now I've drawn a very quick sketch on there. Which, let me just quickly sketch it, because then you'll see how it all ties together. Now again, I'm going to cheat it like I did in the last one and not sketch the full thing. I'm not going to be very official with this. So, I've got an xy axis there. I've got my 1 point is at 1, negative 1, negative 2, negative 1, negative 2 down here, negative 1, negative 2, alright? And my other point is at 1, 2. 1, 2 up here, 1, 2, right? Those are my 2 points. One of my roots, because there is no c value in that cubic that I've got, has got to be 0. Okay? My other 2 roots, you can see that you can solve it. And then what I get, just very quickly, this one is a local minimum, so it's got to come down and then go up. This one's a local maximum, so it's got to go up and then come down. Oops, missed it. And it's got to pop through my root. And it's somewhere there it's got to cross, and somewhere there it's got to cross. Awesome. There it is. Not sketched. Not 100% sketched. If they said for you to sketch this, I'd use all of those ideas, right? But then I'd also have to find the two roots of the cubic. I need to know what this coordinate is and what that coordinate is. I already have the y-intercept there. Are you with me? Awesome. So that's my cubic. It's a very rough one, and using the second derivative to decide if it's a local minimum or a local maximum. Okay, this doesn't always work, all right? Sometimes if you're, like I said, if your second derivative is 0, you're going to have to revert back to the table method. So that's why this is an extension. You don't really need to use this. The table method will work perfectly for this one as well. Try it with the table method, in fact. At the bottom, I've got some problem solving using this stationary points. Just my tips. Draw a picture, because 9 out of 10 times you'll be modeling real life situations, a volume, if it's cubic, a volume, if it's an area, maximization or optimization of an area, that will be a quadratic or something like that. Okay, create the equation, differentiate, solve the stationary points, decide which stationary point is valid. For example, if this is the volume, I'd say, where was this volume maximum? Well, that one's not valid, because you cannot have a negative volume. Only that one, so that one would be valid. Alright, okay, hope this helps. Go check out some more. Remember, I'm here for you.